So what we want to talk about today is just a basic function with square matrices, and it's called a determinant, or collectively called determinants. All right, to see where this gets started, this might seem a bit confusing. Don't worry too much about the details. It's mostly what I want to point out at the end. But let's look at a general 2 by 2 system, okay? So I just have these coefficients, but I'm not going to give them numbers. I'm just going to call them A, B, C, D, E, and F. And I'm going to see if I can come up basically with the formula that will solve any 2 by 2 system. And so we could go through this just like we've been doing with matrix reduction. It's just we don't have actual numbers, so we're going to have to do a bunch of algebra. And here's where it might get confusing. Don't worry too much about it, but I get my 1, and then I get my 0, and then I get my 1, and then I get my 0. And so after I reduce it, I end up with these crazy looking expressions. So what that's saying is that a general formula for the solutions of a 2 by 2 system look like this. Now the question is, can something go wrong with this formula? Remember, sometimes we get no solution. What is it from these equations that I have written right here that would tell you that you have no solution? I'll give you a minute to pause to see if you can think about what I'm trying to get at. But what could go wrong here? So just remember, in general, in math, we can't divide by 0. And notice that both of these have the same denominator, AE minus BD. So things are going to break down if that denominator, AE minus BD, is equal to 0. So what else can we say? We can say that we do get a solution. We will be able to calculate these two numbers if that quantity, AE minus BD, is not 0. All right, and so in a way, that quantity AE minus BD determines the behavior of that entire system. And we're going to see in just a second, that's what we call the determinant of a 2 by 2 matrix, is that quantity AE minus BD. And so the reason for that terminology is that whenever we talk about systems, that quantity is determining the behavior of the solutions. So now looking back, whenever we got to our augmented matrix step, you got to remember an augmented matrix is really shorthand notation where we're gluing two separate matrices together. We have the matrix of the coefficients, and then we have the matrix of the variables, and then we have the matrix corresponding to the right-hand side of that system. And then notice that that quantity that we got, AE minus BD, like that only had to do with this matrix of the coefficients, okay? And so that quantity right there is derived from a 2 by 2 matrix, all right? And so and in general, we'll talk about how to do this for square matrices. It's just I wanted to point that out, that whenever we're looking at the augmented matrix, it might look confusing that we're saying 2 by 2. But you got to remember, whenever we're talking about the size of the system, we're just referring to variables and equations. But so we'll talk with this operation for determinants is going to be an operation for square matrices. And then whenever we connect it back to systems, we're just talking about the matrix of coefficients. And it's an interesting thing. The behavior of a system only depends on the coefficients on your variables. It doesn't depend on what the numbers that you set the equations equal to are. These numbers over here determine what the actual solutions end up being, but in terms of the general behavior of whether or not there's a solution, it only depends on the coefficients. All right, so some vocabulary and notation, and then our first actual definition. But again, whenever we're talking about determinants, we're talking about square matrices. All right, and then if we want to denote its determinant, there's two different ways to denote it. There's basically you put it in absolute value bars, but just be aware determinants aren't always positive like absolute values are. I often use this notation where you say basically abbreviate the word determinant, so a determinant of A. All right, now what we just saw, now don't get your letters confused here. This is just standard notation. So I know I use C and D in different places up above. But for a 2 by 2 matrix, like that, then it'll have this general form. It'll be square, and the determinant is this formula AD minus BC. That looks a little confusing, but if you look carefully, this first part is AD. That's this diagonal product right here. And then be careful, you subtract in the middle, and then you take the other diagonal product. So just as a quick example here, say I have the matrix 3, 1, 6, 4, like that. Then the determinant of that matrix, I subtract the cross product. So first I do 3 times 1, so that's going to be 3. And then I subtract, and I subtract the other cross product. That would be 24. And so that's going to be negative 21. So notice that that determinant is negative there. One interesting thing about determinants, if you look back to that general formula and where I first derived what a determinant is, it was the denominator of the solutions. So if you've ever wondered as you're solving what kind of weird denominators are going to show up in my calculations, it's going to be probably the determinant. Sometimes because of fraction reduction, it'll just be a factor of the determinant. So what this is saying right here is that if this was your coefficient matrix of a system, the denominators of all your solutions are either going to be 1 or 21 or 3 or 7, all the factors of 21. And they may be positive or negative, so these could be pluses or minuses. But these are the only denominators that could show up in a solution. Now, it seems like there would be this natural extension to larger matrices. There is an extension that ties into 2 by 2s, but it's not quite so simple. And so just imagine trying to get that general solution for a 3 by 3 system. Your augmented matrix is going to look like this. You're going to go through all that reduction that I did in a minute ago to try to get it down into the Gauss-Jordan form. Think about how complicated these expressions would end up looking. So you would expect some pretty complicated expressions, and to get a method to find those denominators is pretty complicated. Now that is one way you could do it. I don't advise doing it. And so there are several methods that for computing determinants, but there's one basic one I want to make sure and cover, and it's called row expansion. All right, and so that's the basic technique that I'll show you. There's also column expansion that I'll show you how you could do that. But there's other techniques you might read about if this one seems confusing. You just need, whatever technique you use, you need to make sure it'll work for any size matrix. This is going to seem abstract right now too, because of we haven't even talked about doing matrices. But if you go and read and you're looking at some method that uses these kind of curly patterns like this, I advise against that one because it only works for 3 by 3 systems. It doesn't work for larger ones. All right, and so the main technique that we are going to use is, like I said, it's called row expansion, and I'll have to explain that in our next slide. Real quick before I go on though, I almost forgot to mention, so we're going to talk, I'm going to start with what's called row expansion, but this is more of a general technique called cofactor expansion. So you'll hear me talk that term here very soon. So a real quick notational note that might seem a little bit silly to mention, but just in terms of notation for determinants, especially if you're using those absolute value bars. So I could have a matrix A, and then I could refer to its determinant just by this notation for the determinant, or I could just write the matrix with those absolute value bars on it. All right, it'll just help you understand some notation. One other thing I wanted to point out is you got to be careful, especially whenever there's negatives to do to the determinant. Remember that we subtract the cross products for a 2 by 2 determinant, right? And so just be careful with, because of that subtraction, we have 2 times 6, but then we have minus negative 1 times 3, right? And so that sign in the middle changes to a plus, and so that determinant's actually equal to 15. All right, but the main thing I'm getting at here is a lot of times we won't write this explicitly and then say determinant of A. I might just start a problem with saying 2, 3, negative 1, 6, and then those vertical bars indicate that I'm doing the determinant. So I would do 12 plus 3, which is 15, which we already know. Okay, same thing for a 3 by 3 determinant. So if I have a 3 by 3 matrix, it doesn't matter, that's supposed to be an 8. Like that. Well, what does that mean? Here's my matrix A, and I'm computing the determinant of that matrix. So there's a lot of vocabulary here, but once we actually get to determinants, there's a pattern that's pretty straightforward. But just to explain things, we're going to deal with this idea of what's called a minor determinant. We're going to denote that with a capital M, and we're going to refer to a minor that's in row I, or that comes from row I in column J. All right? And so let me just show you how to do it. Say I wanted to do M1, 2. Okay? And so that's the minor from row 1 and column 2. Okay? And so the way I do this is, first of all, I find the entry in row 1 and column 2. So that would be this 3. And so I'm going to multiply by a 3. All right? And so there's just going to be that 3 because of that entry right there. And then what I do is I cross out that row and that column like that, and I look at what's left, and that's going to be my minor determinant. And so my minor determinant is going to be a 2 by 2 determinant, negative 4, 5, 1, and 2, like that. All right, so it's always entry times the determinant of what's left after you cross out that row and column. And now just to get some refresher on determinants, so that's going to be 3 times, and then I do the difference of these cross products right here. Just be careful with signs. And so I'm going to have negative 8 minus 5. That's 3 times negative 13, which is negative 39. Okay? So why don't you see if you can compute M3, 2. So why don't you pause it a second and see if you can do that. All right, so I redrew my matrix there, took out all the previous writing. So we're doing M3, 2. So make sure you realize we're in row 3 and in column 2. So my entry is row 3, column 2. It's this 8. So the first thing I'm going to do is just multiply by 8, like that. And then I'm going to get a 2 by 2 determinant in this case. And so what I do is I cross out its row and I cross out its column, like that. And so then what determinant or matrix is left? 2, 1, negative 4, and 5, like that. And so what am I going to get? I'm going to get 8 times 2 times 5, that's 10, minus 1 times negative 4, that's negative 4. So be careful of signs here. They're going to cancel and make a plus. And so I have 8 times 14. What is 8 times 14? 32, carry the 3, 112. Okay, like that. So notice what I've done. One thing I've done, and the reason for this terminology with minor, is I've started with a 3 by 3, and all of a sudden I'm computing 2 by 2 determinants. And that's going to be what's called a recursive process. The way we're going to compute determinants of 3 by 3 matrices is we're going to use 2 by 2 determinants. If I needed to do the determinant of a 7 by 7 matrix, first I would do it in terms of 6 by 6s, but then each one of those would be done in terms of 5 by 5s and so on down the line. So it can get pretty cumbersome. Okay, so we're leading into a method for computing determinants that's called expansion along the first row. And we'll see later that we can do this actually on any row and any column. But the idea is to get started is to compute the minor along the top row for a given matrix. In this case, this is the matrix that we'll use. Okay, and so since we're on that top row like that, that means that my row number is always going to be equal to 1. And notice that there's 3 columns. And so the minors that I'll need to compute are M11, M12, and M13. Okay? So Let's get started on M11. So that's going to be the minor in row 1, column 1. So it's using this 2 right here. And so I'm going to multiply by 2 out front. And then just so I don't have to redraw this from my software. And then what I do is I imagine crossing out its row and column and looking at the matrix or the determinant that's left. And so I'm going to take this entry and multiply it by this determinant right here. Let me get all that stuff erased first. Okay, and so so what I do is I take the entry and I multiply by its determinant by crossing out its row and column. Like that, and so you can see that I get 2 times, I do the cross products, remember, and subtract them, and so I have negative 12 minus 40. That's 2 times negative 52, which is negative 104. You see that? Why don't you try to pause and see if you can do the next one, M sub 1, 2. Okay, so hopefully you paused, but if not, so we're in row 1, column 2. So that's row 1, column 2. I'm going to use that 3 as my multiplier, and then I'm going to cross out its row and column to get the resulting minor determinant, or to get the resulting determinant. All right, and so I'm going to compute 3 times, and then its minor determinant is negative 4, 5, 1, negative 2. So I have 3 times, I do the cross product, so I'm going to have positive 8 minus 5, which is 3 times 3, which is 9. And there's a method to this madness. We'll see why in just a minute. Okay? Now, to do M13, now we're in row 1, column 3. So here's our multiplier. Cross out its row and column, and here's the resulting matrix that I need to do the determinant of. And so what do? I do 1 times, and then its resulting determinant is negative 4, 6, 1, and 8. Okay, so I have 1 times negative 32 minus 6, which is negative 38. Okay, so those numbers seem like a bunch of gobbledygook, and this might even be even more so. But let's kind of combine these 3 numbers, but we're not just going to add them. Let's do the first one minus the second one plus the third one. Like that, just for the heck of it. Okay, and so we got negative 104, and then we're going to subtract that middle one, so it's going to be minus 9, and then plus M13, but remember that's negative, so it's going to be plus negative 38. If you go and calculate, if you go and add those together, I believe we're going to get negative 151, correct? Okay, so that seems like an exercise, but guess what? That's actually equal to the determinant of the matrix that we would have been looking for. So the determinant of this matrix is actually equal to negative 151. All right, so that's how we're going to compute determinants. We're going to expand along the top row, and then we got to combine those 3 numbers. We have to use that sign pattern that we add, then we subtract, and then we add. All right. All right, so the basic technique that we'll use to compute determinants for larger matrices than 2 by 2 is that we'll talk about expansion in the top row. And we'll generalize this to be able to expand along any row or any column. Where that's helpful to know how to do is if you have zeros that you could take advantage of to make the calculation simpler. But the basic way to do it, to do the determinant of a matrix that's larger than 2 by 2, is I compute the 3 minors from the top row, and then I combine them by following this pattern. It's basically a plus, a minus, and a plus pattern. Now this formula right here is for a 3 by 3. If I had a bigger matrix, then I would just continue that pattern. So then I would do minus M14 plus M15 up to however many columns I have. Okay, so we can generalize it. So let's try this with an example. Why don't you, uh, once I have it written, why don't you pause it and try it to see if you got the right idea? So here's our matrix that we're going to work with. Again, you might want to just pause it and see if you can work through it. The key thing is this video, I'll be honest with you, I've had to edit a few times because I was talking and not paying attention, and I've made a couple mistakes on that last example getting started. So be careful going through it, and take your time, especially as you're just learning it. All right. Now, so hopefully you paused it and tried it, but I'm going to go ahead and move on. Now, the way we really usually do this is we just go ahead and do this all at once. And so I could talk about my determinant. So just think about what the first step would be. It would be to compute M11. That's this entry and then the resulting minor from that. Okay? And so usually we don't have to break it in. You can, if it helps you for sure, compute each one of these separately like we did in that last example and then combine them together the way we did. Typically when we're doing them by hand, we get used to it and we can just think about crossing things out. When I'm in class, I can put my hands over the matrix so it's easier to see the crossouts. But I'm taking that 3 in row 1 and column 1, and then again, like I mentioned a moment ago, I'm thinking about crossing out its row and column and getting that resulting minor determinant. So that's going to be the determinant 0, 3, 2, -1. Okay? And then notice in my second step, I subtract, and so I'll just put a minus there. And be careful with signs. So I have a minus from my formula, but then notice the entry in row 1, column 2 is a -1. And so I'm going to have a -1 there. Like that. And then I multiply by its corresponding determinant. That corresponding determinant is going to cross out that row and that column. And so I think I messed up where I'm going to, but so you think about crossing out that row and that column. So I have the determinant 4, 3, 0, -1 left. Okay, here's where I was talking about I messed up. I didn't erase that, so I'm going to have to go back and fix that. Okay, and now we're ready for M13. So my entry, some people call that the pivot. And so your entry is at 2, so I'm going to multiply by 2 and think about crossing out its row and column to get that resulting determinant. And so I'm going to have plus, because of the pattern, plus 2 times, and then the resulting determinant here is 4, 0, 0, 2. Okay, now we're ready just to calculate. So we have 3 times, we do this determinant, it's going to be 0 minus 6. And then here these two minuses combine into a plus 1 times. The determinant here in my second part is -4 minus 0. Okay, and then in that third part we're going to have plus 2 times, and then we have 8 minus 0. Okay, notice our calculations are a lot simpler with those zeros, right? And I'm going to point something else out in a minute. So we have 3 times -6 plus 1 times -4 plus 2 times 8. So that's -18 minus 4 plus 16. What is that? 12, -6, right? Okay, and so there's our determinant. Now, one thing to notice about this are those zeros in that matrix. And so notice that it made computing parts a lot simpler, right? The only thing that could have been simpler is if one of these numbers had been a 0, or even more than one of those would have been a 0. Then we wouldn't have even really had to worry about computing the determinant part of it, because we'd be multiplying that by 0 anyway. That would give us zeros. So I would try to get comfortable with expansion on the top row before I talk about this, but I'm going to show you how if you spot some zeros, we could actually end up expanding along this first column if we wanted to, or we could have expanded along this second row if we wanted to, if we understand a deeper concept. And it works the same way. You just do your minors along whatever row or column you deal with. The thing is often the sign pattern is plus minus plus. Sometimes it reverses. It depends on whatever row or column you're expanding upon. All right, and so there's a couple ways you can approach it. If you get comfortable with just expanding on the top row, feel free to compute determinants that way. All right, but if you want to do some pre-thinking and understand, take some time to figure out how this sign pattern works, then you can take advantage of zeros to end up having them be the multipliers out in front. So yeah, if you want to just get comfortable with expanding on the top row, you don't really need to worry about this part, and you can forward it ahead to wherever I talk about larger matrices. But the idea is that in that last example, we talked about expanding on the top row, but we can actually expand on any row. The key thing is to keep up with the sign pattern on the row. All right, so in our last example, we expanded on row 1, and so we have this sign pattern. If you're not understanding what I mean by that, we did M11, and then we did minus M12. So that minus is right there. And then plus M13 and on down the line. Okay. Now, whereas once I go to row 2, if I want to expand on row 2, the sign pattern reverses. Okay. And so what that means is that I would do negative M21 plus M22 minus M23 and if it's bigger, keep going from there. Okay, so the deeper concept here is that if I expand on an odd number row, we get that sign pattern just like row 1. Okay, but if I expand on an even number row, the sign pattern reverses around. Okay, now, and the nice thing is it's the same for columns. Okay, so if I expand on I can expand along columns first of all, and then if I'm expanding on an odd numbered column, I get the plus minus plus pattern, and then if I'm expanding on an even numbered column, the sign pattern reverses around. So let's look back at that last example and see if we can find a better place to expand on it. And I realized even saying the word better isn't necessarily better, but it's just it shortens up the calculations if you spot this kind of stuff. So the key thing to notice here is that there's these two places where I have zeros in my matrix, on the second row and on the first column. Okay, like that. So I could expand on that first column. That green's not showing up very well to me, but I'm colorblind too. But I could expand along that first column, and so what that means is I would use the sign pattern plus minus plus, and so I would do this first minor, and then minus the second minor, and then plus the third minor. But I'm going to have that 0. I want to show you also how we use that different sign pattern. So I'm going to expand on that row there. Okay, so I'm going to expand along the second row here, like that. Okay, so I treat it just like I do with the expanding on the first row. I would take my first entry and then multiply by its corresponding 2 by 2 matrix, where I imagine crossing out its row and crossing out its column, right? And so I would be multiplying by the determinant, negative 1, 2, 2, negative 1. Okay, like that. Just leave some space and I'll talk about the sign pattern here. And so now I would go to my second entry. Since I'm expanding on the second row, I would go there, and see, this is where you're taking a little bit of advantage here, because you're going to have 0 times the determinant, but really who cares, because I'm just multiplying that by 0. So I don't really need to worry about what that is. And then for my third entry, it's right here. So I'm going to have 3 times the determinant, 3, negative 1, 0, 2. Okay, the only thing is I'm using the second row here. That's an even row, And so that tells me that my sign pattern is minus, plus, minus. And so that means I do minus on the first uh, minor determinant, then plus, and then minus, like that. So now I'm ready to compute. I get negative 4 times this determinant, which is 1 minus 4, plus 0, and then minus 3 times this determinant, which is 6 minus 0. And so here I have negative 4 times negative 3, and then plus 0, and then minus 18. And so you see we get our negative 6. Okay, so the nice thing about this method for computing determinants is it extends to larger matrices. So notice this is a 4 by 4 matrix right here. But you can use the exact same idea. It's just going to be a lot of calculation. But the key thing is, and this is the whole idea about how we solve systems too. It's a general method that can be applied to any size system. So we're still going to do the same thing here. And you might want to look at this matrix, and if you notice you have those 2 zeros on the last row, or you have those 2 zeros on the third column. So you could expand along either one of those, but since this is a little bit of a jump, I'm just going to use the first row idea. And so the idea of the first row is to do this determinant. It's going to be you're going to just take each one of the minors along that top row, like that, and then the sign pattern on the top row is plus, minus on down the line. And so it's just the first one is the plus, and then you have minus, plus, and minus. Okay, like that. Now it gets a little bit more complicated, and there's a lot more calculation here. You're not going to like determinants of larger matrices, I'll be honest with you. But it all works the same, and that's the key thing, is just it all works the same. And so we get our first entry on the top row is that 3. Okay, and so I'm going to multiply by 3. Then I cross out its row and column, and I'll have this determinant I have to compute. So I'm reducing it down to a 3 by 3. Now we're also going to have to do this one by row expansion as well. So like I say, it's going to get complicated. I'll only give you one of these in the homework. But in general, this is just the standard way to do it. So we have 3 times the determinant, 0, 3, negative 1, 2, 3, 4, 0, and 2. And then minus, now we go to the next entry, which is the 1, all right? And so we're going to have minus 1 times its matrix, determinant matrix, which would be 2, 3, negative 1, 5, 2, and 3, and 0, 0, and 2. And then we just carry on. Notice here's something nice, though. Our next entry is a 0, and so we would just follow that sign pattern, so it's going to be a plus there, but we got 0, and here's a determinant, but who cares what it is, because I'm going to multiply it by 0. So save yourself some time. Don't feel like you have to write that out. And then for our last entry, remember the sign pattern. It's plus, minus, plus. So we'd have a minus out here. And so to do this part, we're going to have a minus on that 4. So we have minus 4 times, and then its resulting determinant is 2, 0, 3, 5, negative 1, 2, and 0, 4, and 0. Okay, so one thing we get to take advantage of is that 0 on the outside, so we don't have to worry about that part. But now, what do we have? We have these 3 by 3 determinants to compute. So you might want to pause and see if you can work through the rest of this. I'm going to go through it kind of quick. One thing to point out too is that for any determinant, each individual determinant, you can expand on any row and column. So on this first matrix right here, I have that 0 on the top row, so I'm probably going to expand it on the top row. But in this second matrix or determinant right here, I have these two zeros on the bottom row. So I'm probably going to expand on the bottom row for that one. And looking at this one, I'm probably going to do the same thing with the third one, is I have those two zeros in the bottom row. So if you can get comfortable with that more general techniques for expansion, it can save you some time. The zeros, even if you don't, even if you expand this on the top row, there's going to be this zero here that'll shorten it up. But also those zeros will show up in the middle of the calculation. So it'll save you, it'll still save you time, no matter how you go about doing it. So let's see what we can do with this. If you want to, you can just treat this as 3 mini practice problems, since we've only done 1 or 2 examples of 3 by 3s. But let's see what we can do this without all the crossing out and stuff. So for this first matrix here, I'm going to expand on its top row. So that 3's are going to be multiplied times the result, but I'm going to have 0 times, it doesn't matter what that is. And then minus, remember that I'm using the top row, so it's plus minus plus, minus 3 times its minor determinant, which is negative 1, 3, 4, and 2, and then plus negative 1 times negative 1, 2, 4, and 0. So there's my first determinant I have to calculate. Now I just move on to the second one here, and so I have that minus 1 out front. And now notice I'm going to expand on the bottom row for this determinant right here. And you don't have to. You could expand on the top row. You could show yourself that you get the same thing. But the key thing is here, I'm on the third row, so that means I have the plus minus plus pattern. But notice that I have those two zeros, so I have plus 0 times it doesn't matter, and then minus 0 times it doesn't matter, and then plus 2 times its minor determinant, which is 2, 3, 5, 2. Okay, so we're almost there. Now we just go to the third one, and again on this one too, I'm going to expand along its bottom row. Again, you don't have to, but we have minus 4 times the first multiplier is 0. Now we're on the third row, so we got to use plus minus plus as our pattern. So minus 4 times its minor determinant, which would be 2, 3, 5, 2. Okay, like that. And then plus 0 times its minor determinant, so it doesn't matter. So we're making good progress here. We just got to keep going. And so we have 3 times 0 minus 3 times negative 2 minus 12. And then minus 1 times 0 minus 8. There's my first part of the calculation. And then I have minus 1 times 0 minus 0, and then plus 2 times 4 minus 15. That. And then I have minus 4 times 0 minus 4 times 4 minus 15 plus 0. Okay, so we're almost getting there. So we started here, we just got to here, we just got to finish our calculation. And so we have 3 times, this is negative 14 times negative 3. I got to think about that. Negative 52 or positive 52, right? And then here I have minus 8, and so that's going to be a plus 8. All right, and then I have minus 1 times, this is 4 minus 15, so that's negative 11, so I have negative 22, like that. And then I have minus 4 times, this is 4 times, or 4 minus 15, which is negative 11 again, times negative 4, that's positive 44. Okay, we're almost there. Gosh, I hope I'm not incorrect here, but 3 times 14 is 42, right? Okay, so we got 3 times 42 plus 8, and then plus 22, and then minus 4 times 44. What is that? 16, carry the 1, 176. Let me pause and check my calculations there. So yeah, I was all good. That was 176. So we got 3 times 50 plus 22 minus 176. After all that work, guess what we end up getting? Negative 4. And that is the determinant of the matrix that we just started with. Okay, so I know that was a lot of calculation. Hopefully you can at least pause and rewind and go back through and see a little bit more carefully. I did double check this and by using some technology, so it is correct. And so the key thing is it's easy to get lost. So make sure to practice the simpler ones first, and then just take your time going through the calculation. And remember, if this idea of looking and expanding on different rows and columns and stuff is confusing, you can always expand on the top row and do each one of them the same. All right, I hope that helps. Good luck.